So the one thing that we didn't talk about is actually the most important thing, right? So the one operation that makes or breaks your queries is the joins. Joins are where you do most damage. In fact, if you forget a join, you see that you generate so many tuples that even the simplest possible database, you can do a lot of damage. So joins are very, very costly, and it's going to be really the main part where you want to optimize. So let's just see a very naive way of doing join. And then we are going to get more and more sophisticated. The algorithms are not difficult, but remember that if you're joining two tables that happen to be both in memory, then this is very easy. If you're joining tables that cannot fit in memory, then you have to do multiple passes over them. So we have to think about how to do that. So little terminology. Whenever you're doing a join, we write it like this, right? So it is going to be important to distinguish between these two, right? So R join S means that R is the inner relation, S is the outer relation. It's just that one is left, the other one is right. It is important because of the cost. This is not outer join, which I hope that one day you learn. So inner and outer relation, okay? So let's think about how you would do join. So the join itself is a nested loop, right? It's an n squared like operation, right? So so the idea is that let's say you have two memory blocks. Okay. So you are going to use one for R and one for S. Okay. So you are going to read one page of R in here. Okay. So this one page of R has multiple tuples, but all of the tuples have to be checked against every single tuple in S, right, to see whether they join. So what I need to do is now read one block of S, see if they join. If they do, put it in the output buffer. Read the next page of S, do the join, put it in the output buffer, and complete all of this. To be able to do that, I have read S completely once, right? Okay, now I am done with that one page of R. Now I'm going to read the next page of R, and I'm going to do the same thing again. Basically, this is a nested for loop that I messed up. That looks like this, right? So basically, for one page of the outer relation, I actually did that wrong. This is outer, this is inner. I'm getting rusty. Okay? Read it, and then read the S completely, and then continue, right? Okay? So basically, I read one page of R, I read all of S once, and I keep reading all of S as many times as there are number of pages in R. So basically, I read S pages R times. Whereas I read R only once. And this is the important thing, that in every single join you see, the outer relation you read only once. Okay? But the inner relation you may end up reading many times. So the total cost of this is pages of R, because I read R exactly one time, and then pages of S times pages of R. Because I read S completely this many times. Okay? So the point is that I do this because I'm really doing I'm using, again, only 2 blocks to do a join, but joins are very costly, and this can be huge, right? So if you, let's say, pages of R, so let's say pages of R is 100, and pages of S is 200, or let's say 2000, then the total cost is 100 plus 2000 times 100. So that is 200,100. No, this is 20,000. No, that's right, right? Right. Now, would it be different if I were to switch them? What if R was inner and S was outer? So what would be the cost? So what about cost of S join R? But I do the same way. But now I read S only once, right? So read S once, so which is 2000, and then read R 2000 times. So 100 times 2000. So this is actually 202,000. So it does matter which one is inner, which one is outer, right? Actually, what happens is that it's always best to have a small relation to be the outer so that you don't iterate through the inner relation many times. But I can do better because this is very naive. Why do I have to use only 2 blocks to do my join? What if I have more memory? If I do have more memory, I can use something else, something called block nested loop join. So let's say I have m blocks again. I am going to do it slightly differently. I am going to use m-1 blocks for R and only 1 block for S. The algorithm is exactly the same. Now read R, but read m-1 blocks of R in memory. So you have many more tuples of R. Then that means for every tuple of S you read, every block of S you read, you will join with everything in there. And then you will continue doing the same until you are done with S. Now once you are done with S, this m-1 blocks of R, you're done. You process the join. You never have to read them again. So then you read the next m-1 blocks of R, right? You keep repeating this until you are done with R. So in the block nested loop joining, we are doing exactly the same thing, except instead of reading 1 block at a time, I'm reading multiple blocks. So that means I actually have to read S fewer times, because instead of reading 1 block of R, I'm reading m-1 blocks. So now I need to read S, actually, as many times as it takes to fill this one. So pages of R, m-1 ceiling times, right? So let's say, for example, so my total cost would be, remember that you read R again only once. So now the total cost in this case is pages of R plus pages of S like this. Okay. So let's look at the same example as before, that I had pages of R was 100 and pages of S was 2000. Okay, and I want to look at R join S, and let's say M is 51. I'm doing 51 for simplicity. Okay, so that means I can read R into 50 blocks and then read S. How many times do I have to read S? How many times do I have to read S completely? Following me? Twice. So it's 50 blocks. I can read half of R, read all of S, right? And then read the other half, all of S. So I'm reading S only 2 times. So 4,000 plus 100, 4,100. Okay? The same thing is true. If you were to switch S and R, you would get a different cost. So let's say I actually have less memory. So I have 21. So my total cost in this case, same deal. So you have 100 plus 2,000. Now I have to read S how many times? 5. So you have 100 divided by 20, right? So now this becomes 10,100, right? So you see, it does scale quite a bit. We started at 200,000. By using just a few disk pages, I'm able to get a significant cost reduction, right? So the block nested loop join is just a simple way of showing you by using the memory that you have. And you know, the memory is getting cheaper. You're getting bigger and bigger memories even on your laptops, right? So it's not going to be outrageous that you have memory available. So just by using more memory, you can do better. It turns out that block nested loop join is easy to explain and easy to write questions for, but most databases will use things that are definitely much more sophisticated than that. So one thing that I know, for example, Postgres, you are going to actually do a homework where you have to see the actual query plans. And Postgres uses very, 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 very frequently something called hash join. Now, hash join is actually very easy to explain. Remember that hash is always divide and conquer. So you're going to take your relations and you're going to hash them with respect to whatever you are joining on, right? So if you have, for example, R join S on R.A is equal S.B, right? So your job is to find tuples in R and S that join on attribute A of R is attribute B of S, right? So what I would like to do is, so you will have some number of blocks, right? So M blocks. So basically I'm going to use, hash into M buckets. So I'm going to first read R and hash into M buckets using R.A, right? So hash on R.A. Then read S, hash into M buckets, the same M buckets using S.B. So now you have hashed the tuples that might join into the same bucket. So if you're going to really join, think about a bucket as basically comprised of first the R tuples and then the S tuples, right? So all you need to do is read a bucket back into memory and do the join. So then read each bucket into memory and join. Okay. Now the cost of doing that will very much depend on what the sizes are, right? So, so let's say, for example, let's use the same idea here. So we have pages of R is 100, pages of S is 2000 and M was 51. Okay. So if I'm going to take all of these and hash to roughly 50 buckets, right? So I am basically mapping 2100 pages into 51 buckets. So how many disk pages per bucket, roughly? If you assume that it's equally likely, that's about how many pages? 4, right? Roughly 4 pages per bucket. So if I actually have done this, is it possible for me to read a whole bucket and then do the join within here? Yes. I have 50 pages. I can read 4 pages for sure, right? So that means I can basically, read R1s, hash and write, right? And write once because of hashing. Read S1s and write once, hashing. Then when I'm reading the buckets, I'm again reading the whole relation back, right? So basically, I'm reading R and S once back, hashed version. So the total cost of this is basically read once, write once, read write one, and read once. So you read, written, and read again. So it's 3 times the total size, so 2100, which is what? 6,300, right? So this is kind of the general idea that by hashing, you can now divide and do something like this. Now, what you may find is that if you just hash to 20 buckets, this can actually be better than the cost with just block nested loop because probably hashing will work better. So if I had, let's say, if M was, what was the other one? 21. So I would basically have about 2,100. So okay, I'm going to give up on that one. Well, let's try this. So I have 2,100 pages and 21. So I have about, 100 pages per bucket, right? So basically, I read once and I wrote once. So that was, the total cost was 2 times 2,100. So 4,200 pages just to hash. But unfortunately, I cannot really read 100 pages all in memory and then do my join, right? So this is now the point where, what do I do for this part? So I have a bucket, but I cannot really read the whole thing. So what happens is that in this case, for this part, you actually end up doing a block nested loop join. So basically, you would read the R part in a group, and then you would read S time once. So you can probably do that still in one round, because the R bucket, the R part of it is actually very small, so you can probably still do it in one pass. So you can probably do hash join again, only at 6,000, as opposed to the 10,000 we found, right? So the idea is that if a bucket doesn't fit in memory, then do a block nested loop join. Now, I will not bore you why, but this would still be, the total cost would be 6,300. So it kind of becomes hard to explain, and I don't think it's worth going into all the details. But Hash join is, again, it gracefully increases in cost because you can use tricks from different operations. If you don't want to do hash join, the other trick that we have is sort merge join. Again, that's also easy to remember. So let's say I have r dot a is equal to s dot b. So sort r on r dot a, sort s on s dot b. Now, if they are sorted, all you have to do is just read them in one stream and do the join. So after this point, you can still basically do the join in one pass. Okay? So the idea would be that now you have sorted R. This is not the actual R, but a sorted copy that you stored on disk. And you have sorted S on disk. Okay. And now, of course, you can do a very simple thing. If you're going to join, so let's say you have a tuple here with r dot a is equal to 1. If there is no s dot b equals 1, you know that no tuple will join, right? So that's the smallest value. So now you know. Or if there's a join, you produce the join, and then you are done, right? So then you move to the next tuple. Let's say r dot a is equal to 4. Again, now if the smallest tuple here is less than 4, you can disregard because there's nothing that will join. And then until you find equals 4, if you find 4, then you basically join. Otherwise, you disregard the join. So basically, you can, it's like popping smallest value from each until they do join. Now, if you have memories of CS1, data structures, algorithms, this is, again, almost identical to the merge step of sort, right? I'm just merging to find the same value, not exactly one greater than the other. So this merge step can be very efficient if there is a single value for a given A and a B value, right? Because you know that there cannot be multiple. But often what happens is that you are joining values that can have many, many different values, right? So it could be that, you have r dot a is equal to 1. So you have, 1, 2, 3, 4 in R. But then you may have many ones and twos here, for example. So if you remember, when you do a join, that means you take this tuple and you produce a tuple for every single one value here. Only then you're done. Then you read the next one. And then you join for every single value here. Which is still not so bad because you only will have one tuple here, right? And you will iterate over this one if duplicates are allowed until you are done with the ones. What would happen is that if you had duplicates on this side too, well, now you have a nested for loop, right? So for this one, you're going to join with all of these. Then this one, you're going to join with all of these. So now, this is becoming a block nested loop join on the equal values. Okay? So let's put that aside because if you cannot put this part in memory, then sort merge join will also be complex. But generally speaking, assuming that that does not happen, you can generally do this with cost of sorting S, cost of sorting R, plus one pass over R and S. Read R once, sorted version, plus read S once. sorted version. So this assumes no duplicates. And not only that, after you sort, to do this, you only need 2 disk pages. You don't even need a lot of disk page. And that, in fact, since it is sorted, if you have an order by later on, the order by is free because it's already being produced in the sorted order. So the sorting early on may actually help many other operators above. If you have a group by, that's also great because this is already being produced in the, if it is group by r.a. Okay, so let's just do a simple operation. One example, and then I will be done with this. So let's now say pages of R is the same example I had. So what was it? This is 100. Pages of S is 2000. And let's do M is equal to, use 51 or 20? Let's just use 51. Even though it's 51, I'm going to treat it as 50 because my brain is not that strong. So, all right, 51. So I'm going to read R, sorted and write, right? So I'm going to, for 200, create 2 groups. So then I can read those 2 groups, sort and write back. I'm writing it back because I'm going to read it to join afterwards. Okay. Then S, I have 4,000, I read and write, and I will generate 4 groups. Then I have another 4,000, sort and write. And then I'm finally going to read them all, merge, do the join, and output. So, which is 2,100, right? So what is the total cost in this case? So I have 8,000, 10,100, 10,500. Right? Are you with me so far? Okay. But of course, you're not going to do that, right? This is how we do it on math, but in reality, you can quickly see something that's happening here. Okay? Let's see if I can. No, that one. There we go. Okay, so I'm wasting a lot of space because here I have 2 groups, here I have 4 groups, right? So how many groups do I have total? 6, right? Now to be able to do the join, I basically need 1 representative from each group because I'm going to find the smallest in R, find the smallest in S, and see if they join, right? I don't need to fully sort at that point. I can just use these groups and then just do the join part. I can just skip the last sort part. That's not so important. I will still be able to produce it with the joined order, joined and sorted order. So I can skip the last part and then move immediately to join. So basically what I can do is merge, join, and last sort step. So technically what I will do is I will basically do the 200 to create 2 groups. I will do 4,000 to create 4 groups. Then I will read all of them once more, which is 2,100, to sort, merge, and join, which actually happens to be 6,300, the same as hashing. Okay? So these operators are defined in such a way that you can actually mix and match their different steps. So this is really what I will do. And in fact, this may scale better because maybe I can even do something like this even for, when the memory gets smaller. But so, sort merge is also very useful, but also, since it produces a sorted order, it may help with other operators up front. So these are basically the different join operators. So kind of take a moment to remember that we have seen many different ways to implement different queries, right? So we have different ways to do duplicate removal. You can sort or hash. Depending on the memory you have, you can do it in memory at once, or you may have to do a sort first or a hash first. For doing a selection, you can read the whole table, and then you can use an index, or you can read the whole table, and then while you're reading the tuples, apply different conditions. Or you can use an index to find some of the tuples, and then read those, if necessary, from disk to find other attributes you need for your query. You have things like distinct and group by, which you can do by sorting or hashing. So every single operator that we have, there are multiple implementations, right? So this brings us to our last topic. And I will only kind of set it up, and then we'll continue next time, which is the point of query optimization. So the point of query optimization is, first of all, you generally buy a database system or use a database system because of two main reasons. One is that it implements your transactions correctly, even if there's concurrency, right? So that you write your program not wondering what other person is doing. You don't have to write the rules in terms of conflicts. That's handled. Two, you write your queries without really implementing it with respect to whatever the data storage is, but the database chooses the best one for you using all the rules that it has. The query optimization, right? And the query optimization is a huge, complex piece of software that is developed for years of programmer time. So it's generally the most important and the most secretive part of a database, and really the reason to choose one database over another. So query optimization is a very complex topic, but we will basically think about the basic steps. So generally think of this as follows. You have a query. You say, select XYZ from RST, where some condition and some other things, right? So, and you've written this, and hopefully this is not a horrible query, because no database will be able to recover from horrible queries. But for the most part, you have not really thought about where the database is stored, if there are indices, those are all going to be important. And given a query like this, what the database wants to do is create what's called a query plan. So the query plan is basically a tree where you have the relations in the leaf nodes. It's not necessarily a balanced tree. And you may have selections, joins, and other operators, such that the root is basically a correct answer to your query. And you may have projections here, and so on. Okay. And then for each of these operators, there's actually an implementation. So it will say, hash join, and there's going to be some amount of memory, hash join, some memory, and this will be, index I1. This will be table scan. So this will be, let's say, table scan. And there could be some things like this one. This could be on the fly. Okay. On the fly generally means that you basically are, doing it as the data is produced from the operation below. We will talk more about that. So basically, the query optimization is starting from that point that you have an SQL query to coming to something that is as specific as this. What are the tables? How are you going to access them? What are you going to do to join? Which order are you going to join? What join operation are you going to use? In which order? Are you going to join RNS first or SET? And then how much memory you're going to allocate? And this whole thing. And these operators are basically all pipelines, right? The same thing we were just trying to talk about early on that I am going to try to find here, right? So this is what we were talking about here, that these are all pipelines. That means that the output of one operator is the input of the other operator, right? So that's why you have the relations in the leaf nodes, and then you read the relations to produce upper level operations. So basically, to get from here to here, there's a whole bunch of steps. Okay, so let's just think about what those steps are, and then we will talk about them in detail on Monday. So the first step is I'm going to parse the query. I'm going to look at system tables to see if you made a mistake, if some things are wrong, and and I can also rewrite the query, right? I can decide that you had a nested sub-expression, but actually that can be made into something else, or I can decide that you had a view. I'm going to take the definition of the view and write it. You had a query in the from statement. I'm going to put that in the where statement. I'm going to do this, and I'm going to look at the Boolean expressions and optimize your Boolean expressions. So, if you have written things that, can never be true, I know that I don't even have to execute that query. All of that is parsing the query. So after I parse the query, I'm going to find what are the indices that I can apply to all the different conditions, right? So find, this is called access paths for selections. So every table, I can do a table scan, or some of them I may have some indices that I can use. All of these have different costs and different types of output. And if you use this index, I'm going to get 16 tuples. If you use this index, I'm going to still have 10,000 tuples to read. All of that is at that point. Then I'm going to decide how to do my joins. Okay. So to be able to do my joins, I'm going to think about all different join orderings. Think about generating exponential number of join orderings. And then I'm going to figure out which ones are good. To be able to do that, technically you will generate them all. But in practice, you will do what's called branch and bound. Have you taken AI? If you're taking AI, you will see branch and bound, right? So the whole point is that you generate some options, and then you look at how costly they are. So we are going to have a cost estimation. Because almost all query optimizers you use are cost-based, meaning that they will try to understand what is the cost of this query up until this moment. If you do this selection and this join together, what would be the cost? Exactly what we were doing here. That's exactly what the database would do. In fact, earlier optimizers were just making some basic heuristic decisions. Turns out that sometimes they can be very wrong. Instead, all these databases use cost-based optimization. To be able to do cost-based optimization, it has to estimate how many tuples will be out in the output even before we actually have the output. Okay, we will see how that's done. And then sometimes when you do cost estimation, you will see that some orderings are outrageous. You don't even need to consider, so you will remove them altogether. So we will see that this is actually, we will use dynamic programming for this one. You see all your programming classes are becoming useful here. And then eventually, basically, you're going to come up with a final final plan, choose the least costly plan. Okay, so this is the cost of query optimization. But there are many other things you are going to consider. Things like sorting may be useful, and so on. So on Monday we are going to see all of these different steps, little things that go into some of these, and then continue on probably with transactions.